Welcome! In the previous lectures, you learned that the earthquake wave travels through the subsoil to the surface and that their characteristics and strength are changed along the way. Today, we'll see how mainly the shallow subsurface and its geological characteristics influence the contribution of the induced earthquakes to the seismic hazard. Let's first take a look at the shallow geology of Groningen. Here you see a cross-section through Groningen from north to south. The length is 40 kilometers and we are looking at the top 25 meters below the surface. This is the very last part of the path the earthquake travels, but also the most important part. Because depending on the soil types the earthquake signal travels through, the signal will be changed. Groningen subsoil in this depth range consists mainly of sands, clays and peats from both the geologically more recent Holocene and the older Pleistocene age. We know this from thousands of boreholes and cone penetration tests in the area. Typical for Groningen are the channels that were formed by the sea. It can also be seen that the south of the area has a different geology to the north. In the south, the Pleistocene soil reaches to the surface, while in the north, the younger Holocene soils can be up to 25 meters deep. Why is it important to know this? Well, if a seismic wave formed by an earthquake travels from the stiffer soils, like rock or dense sand, to weaker soils, like clay and peat, the wave can become stronger. This may lead to differences in the amplitude of the earthquake acceleration at the surface. If the wave, however, travels through weak soils, like clays or peat, the damping effect of the soil may, on the other hand, reduce the amplitude. For Groningen, the amplification over the soft topsoil can differ with a factor of about 2. This image shows the local site amplification across the Groningen region. The orange color shows areas where the amplification is twice as high as in the green area. In current maps predicting the peak ground acceleration that you have already seen in previous presentations, this effect is taken into account. That is why you see these irregular shapes. There is another reason why it is important to study the shallow subsurface. This is the effect of liquefaction. Liquefaction is the phenomenon that the saturated granular soil, such as the sand, loses its strength. You might have noticed this effect on the beach. If you cause a vibration, for example by jumping up and down, the sand behaves like a liquid. This effect is also called quicksand. Well, what happens in the soil during liquefaction? In a normal situation, the sand grains are in contact with each other and the water is in the pores between the grains. During an earthquake, the soil experiences a shear force. Because of this force, the grains want to move closer together into a new arrangement. For the grains to move, the water needs to be forced out of the pores, but this takes a certain amount of time. During this time, which is usually short, the water pressure increases, the grains lose contact, and the strength of the soil is lost temporarily. This is liquefaction. Once the water pressures reduce, the soil particles rearrange themselves in a more optimal pattern and a settlement is observed. Liquefaction has been observed during many, mainly tectonic earthquakes in the past. Following the Roermond earthquake in 1992, liquefaction effects were observed. The effect has not yet been seen in Groningen, because the earthquakes that have occurred so far have not been strong enough to do so. However, if the vibration level would increase because of continuing gas production, liquefaction might occur. If it were to occur, it might cause damage to houses and/or roads. The amount of liquefaction that can occur depends on several factors, such as the density of the sand, the age of the sand, the number of cycles, and the amplitude of the earthquake. By looking carefully at the geology and the presence of the sand layers, it is possible to predict whether liquefaction is a risk or not. For Groningen, most of the loose sands are found in the north of the area. As you have seen, the geology of the shallow subsurface plays an important role in both the site response and the risk of liquefaction. Because of the large amount of knowledge available about the shallow subsurface in Groningen, it's possible to include these two effects when assessing the impact of induced earthquakes in Groningen and implementing effective mitigating measures where necessary. Thank you for your attention.